we are ready to go live. Yeah, that's what I thought. Okay, so Hess's law. Just a reminder, path function, state function. For a state function, the path does not matter. Okay? Only the beginning and the end. So say, for example, you have some reaction going from your reactants at A to products at L, and you want to measure the enthalpy of reaction. But for some reason, it's really, really difficult, and you can't measure this directly. Maybe you just don't have the materials. Maybe it's incredibly toxic. Maybe your older brother will beat you up if you just whatever. The point is, you can't measure it directly for some reason. So instead, you go from A to B, B to C, C to D, D to E, E to F, F to G, G to H, H to I to J, J to K, K to L. Okay? So long as you can get from A to L in some fashion, and it doesn't matter. These enthalpies of reactions will add up to this enthalpy of reaction. Okay? That is Hess's law. If you can get from A to L by some path, then all of these enthalpies will add up to this enthalpy. What that means is that you're going to be adding reactions. But it's not quite that simple. Okay? Because your reactions don't always match up quite so tidy. Right? They're a little bit more complicated than that. You're going to have to put in a little bit of work. So, for example, combining nitrogen and oxygen to make nitric oxide has an enthalpy of reaction of positive 182.38 kilojoules. Nitric oxide plus oxygen, making nitrogen dioxide, has an enthalpy of reaction of positive 82.183 kilojoules. Okay. What is this enthalpy of reaction? Nitrogen plus oxygen to make nitrogen dioxide. Well, you can get this reaction here by combining these two reactions up here. Let me show you. Nitrogen plus oxygen yields 2 nitric oxide. 2 nitric oxide plus oxygen yields 2 nitrogen dioxide. And when you add our two reactions together, anything on either side of the arrow is going to cancel out. Our 2 nitric oxides will disappear, leaving us with nitrogen plus 2 oxygen yields 2 nitrogen dioxide. So adding those two reactions together gives us the reaction we're looking for. Therefore, just as with sublimation, enthalpy 1 plus enthalpy 2 yields enthalpy 3. So that is a nice, simple Hess's law problem. The enthalpy of reaction we're looking for is going to be (182.38) plus 82.183. This enthalpy of reaction down here is positive 264.56 kilojoules per mole. So that is a very simple Hess's law problem. I say simple because they can be a little bit more complicated. Methanol plus oxygen yields CO2 and H2O with an enthalpy of reaction of negative 1452 kilojoules. Methanol methane plus oxygen yields CO2 plus H2O with an enthalpy reaction of negative 890.8 kilojoules per mole. So what is the enthalpy of reaction to go from methane to methanol? This one, a little bit more complicated. Reason being that we have methanol on the reactant side up here. We want it on the product side down here. So sometimes for Hess's law problems, you don't just add, very rarely are you just going to add the two reactions or three reactions or four reactions together. More often, you have to manipulate these reactions to get everything in the position that you want it in and in the numbers that you want it in. Okay. So we have methanol on the reactant side. We need to get it on the product side. In order to do that, we need to flip this reaction around. And when we do that, remember, flipping the reaction means you flip the sign. So, we flip that reaction. It becomes 2CO2 plus 4H2O yields 2CH3OH plus 3O2, and our new enthalpy is positive 1452. Our other reaction also needs to change. Take a look. One methane plus two oxygens yields CO2 and 2H2O. So the methane's in the right place. Methane on the reactant side, methane on the reactant side. The problem is the number. We need two methanes in our final resulting reaction. We only have one up here. So we're going to need to double this reaction. So we hop back over here. Two CH4 plus 4 oxygen yields 2 CO2 plus 4 H2O. We've just doubled every one of those numbers. And when we do that, we're also going to double our enthalpy of reaction. So negative 890.8, we double that, it's going to be negative 1781.6. And now, once again, we add our reactions together. And if we've done all of this correctly, they should add up to the reaction we were looking for. Okay. So we have 4 water down here on the product side, 4 water up here, that cancels. 2 CO2, 2 CO2, that cancels. 3 oxygen versus 4 oxygen leaves us with 1 oxygen. And then methanol doesn't cancel out, methane doesn't cancel out. So our final resulting reaction, 2CH4 plus 1 oxygen yields 2 methanol. And just to double check, yes, that is the reaction we were looking for. Okay. So that is a still fairly simple Hess's law problem. Okay. You manipulate the reactions that you've been given in order to get the resulting reaction you're looking for. Every change you make to the reaction is reflected in the change you make to the enthalpies. You flip the reaction, you flip the sign. You multiply the reaction, you multiply the enthalpy. And then, once you've done that, you just go ahead and you add these guys together. Okay? So 1452 plus negative 1781.6. Our new enthalpy of reaction is going to be, I'm going to use the calculator, 1452, negative 1781.6, negative 329.6 kilojoules per mole. So when 2 moles of methane reacts with 1 mole of oxygen to produce 2 moles of CH3OH methanol, it's going to release 329.6 kilojoules of energy. So that is a relatively simple, still, Hess's law problem. We flipped one reaction, meaning that we flipped the sign. Okay? We multiplied the other reaction by 2, meaning we multiplied the enthalpy by 2. And then, once we did that, we just added them together. Let's take a look at another example. This one is even more complicated, okay? Because we have the combustion of propane, we've got the splitting of water, and then we've got making propane out of carbon and hydrogen. So we've got 3 reactions. That's all. Now, this looks bad, but once again, it's just a matter of getting things where they need to be and in the correct numbers. So let's go ahead and start with this third reaction down here. Why? Well, because it's the only one that has graphite. We need 1 graphite on the left. We have 3 graphites on the right, which means we're going to flip this reaction and we're going to divide by 3. So flipping it means we will flip the sign. So it'll go from positive 83 to negative 83. And then we divide by 3 to get this down to 1, meaning we're also going to divide this by 3. So when we do that, our reaction will be carbon plus, unfortunately, 4/3 hydrogen yields propane, 1/3 propane. I don't know how common it would be to get fractional coefficients like this, but it's entirely possible and it's acceptable. Again, this is a tool that we're using to get to our final result, the answer we're looking for. Okay, so it's okay to fudge the normally accepted rules in order to get where we're going. So when we flip the reaction and divide by 3, our new enthalpy is going to be negative 27.7. There we go. All right, now let's continue. Let's pop back over to this. All right. So this water and H2 and O2, none of those show up down here. Therefore, well, actually, no, the oxygen does. But oxygen is also up here in this reaction. So let's not balance, let's not try and do anything with this just yet. This is going to be used to get rid of stuff that we don't want. So we'll use this to get stuff we do want in a place we want. And then we'll use this to get rid of the random crap. Okay. So this is the only reaction that has carbon dioxide in it, right here. It has 3 carbon dioxide on the left. We need 1 carbon dioxide on the right. So we're going to once again flip this reaction and divide by 3. Flipping the reaction, we'll get the carbon dioxide on the right. Dividing by 3, we'll get this from 3 down to 1. That will give us 1/3 propane. You know what I'm talking about, propane? Plus 5/3 oxygen to make 1 CO2 and 4/3 water. And once again, flipping the reaction, dividing by 3, means we flip the sign on delta H, divide by 3. So 1776 becomes a negative 1776, and then we divide by 3. That's going to be negative 592. All right. Now we can use our last reaction. Okay. We have water and hydrogen to get rid of. Okay. So we only really need to focus on one thing. So let's just look at water. There's no water down here in this final reaction. Okay. So this middle reaction here, we'll be using that to eliminate the water that we have and don't want. Okay. So we look at the reactions we have. We have 4/3 H2O. We want 0 H2O. We have water on the right in this second reaction, as I've written here. We come back over to the reactions we were given. We have water on the left, meaning that this water on the left will cancel out water on the right. We have 4/3. We want to get rid of all 4/3 of that, so we're just going to multiply this reaction by 4/3. Doing that will let us get rid of water. Okay. All right, so we multiply that reaction by 4/3. We get 4/3 H2O yields 4/3 hydrogen, and 4/3 times 1/2 is 2/3. Oops, that's kind of impossible to read. 2/3 oxygen. Okay. And then multiplying our reaction by 4/3 means we multiply our enthalpy by 4/3. I'm going to use a calculator for this one. 228 times 4 divided by 3, 304. We didn't flip the reaction, so we're not flipping the sign. All right. Now we begin the unpleasant process of adding everything together. Okay. So, carbon up here in our first reaction, that's not going to go anywhere. That is going to stick around. It doesn't have anything to cancel out, and we don't want it to cancel out. Okay. We have 1/3 propane right there. We have 1/3 propane right there. It cancels out quite tidily. We have 4/3 hydrogen there. We have 4/3 hydrogen there. That also cancels out quite nicely. 4/3 water will cancel out with 4/3 water, just like we wanted. Our carbon dioxide is not going anywhere, which is good. We don't want it to go anywhere. And then 5/3 oxygen minus 2/3 oxygen. I hope you can trust me on this. 5/3 minus 2/3 is going to be 1. So when we add these three reactions together, we get carbon plus oxygen yields carbon dioxide. So if you're just a little bit careful, you proceed step by step, it should give you the answer that you want, the answer you're looking for. And so when we pull up our handy calculator, we can add negative 27.7 plus negative 592 plus positive 304 equals negative 315.7. All right, and that is the answer. This is a slightly more complicated Hess's law problem, but still entirely effective. It works just fine. So just proceed step by step. Be careful. You flip reactions, you multiply reactions, and then it has built into it, a way to double check yourself. When you're done, you go ahead and you throw. You just go through and add your reactions together to make sure that they add up to what you want. Okay. Hess's law problems are a little bit complicated, a little bit difficult, but if you're careful, you'll be able to get through them just fine. So once again, I'll pause for questions before shutting this down. All right. In that case, we'll take another 5-minute break. I'll come back at 3:15 to talk about enthalpy of formation. I'll see you around.